Hello everyone. Today we will learn about the time response analysis of control systems. What is meant by time response analysis? The response given by the system, which is a function of time, to the applied excitation is called time response of a control system. We know that since time is used as an independent variable in most of the control systems, it is usually of interest to evaluate the state and output response with respect to time, or we call it as simply time response. So basically, the time response of a control system is usually divided into two parts. One is the transient part and another one is called the steady state part. So the two parts you can see here, that is a transient response and the steady state response. The final state achieved by output is called steady state, while the output variation during the time it takes to achieve the steady state is called transient response of the system. So transient response is defined as the part of the response that goes to zero as time becomes very large. You can see here, we can mathematically represent it like this: C of t, that is we generally represent the output as C of t. That consists of the steady state response and the transient response. This part is T of t is the transient part. So the transient part vanishes as t tends to infinity, that is limit t tends to infinity, Ct of t is equal to 0. So the part which remains as time goes to infinity, that is the steady state response. So that is a part of the response which remains after the transience has died out. Transient has died out means in the transient response, it may be either of exponential or it can be oscillation. So these oscillations may die out as time tends to infinity. So in this waveform, you can see here there is a waveform here. The starting point here, that is the exponential part, it dies out as time tends to infinity. So this part remains after this transience has died out. That part is called the steady state response. In this particular example, you can see there is an error between this final output and this steady state. So now, before going on to the time response analysis, we need to understand about the standard test signals, why it is required. So most of the control systems do not know what their inputs are going to be, or that is, we can expect a system in general to get an input which may be a sudden change, or it may be a momentary shock, or it can be constant velocity or constant acceleration. So to do analysis of the system, it is difficult to apply every type of input to the system and then to check the response of a system. So there are certain reference signals called as the standard test signals which we use to analyze the particular control system. So one of that is called step signal. So step signal is nothing but, when you see here, it is like we can just form, it is like it is constant throughout the time. So in x-axis we have time. So generally input we represented by R of t and output we represented by C of t. So here we for unit step function we will be representing it as u of t, and here it is R of t is equal to a u of t, where this a is called a is the amplitude. Means suppose we are writing a ut, means this one is the magnitude a. So if it is like if it is a unit step, means this a is equal to 1. So a ut. Now for mathematical representation of step signal is like this: R of t is equal to a u of t, and u of t is equal to 1. So here you can see that it is equal to 1 for t greater than 0 or equal to 0, or equal to 0 less than t less than 0. So this is our 0. So you can see that it is for t greater than 0, it has the magnitude, and for t less than 0, the magnitude is 0. So this is how we represent the step signal. So unit step signal means a is equal to 1. For a is equal to 1, we call it as a unit step signal. Now for analyzing this time response, what we generally need the Laplace transform of the signal, because we know that the transfer function is generally represented as the ratio of Laplace transform of output to Laplace transform of input under 0 initial conditions. So we need Laplace transform, we can represent like C of s by R of s. So this R of S is R of t is input. So R of S is the Laplace transform of the input. So when you take the Laplace transform of the step signal, we will be getting R of S is equal to A by S. Okay, so this one is for a step signal, we will be using the input as A by S. Next comes the ramp signal. So ramp signal, mathematically it is represented as R of t is equal to A into t. So it is just a ramp, it is a slope. So you can see here it is a slope, and this is t and this is R of t. Now this one is the mathematical representation, and this one is time 0. So you can see that for time t greater than or equal to 0 only we have this ramp. So for t less than, that is towards this side, t less than 0, it is 0. Output is 0. So R of t is equal to A into t for t greater than or equal to 0, and is equal to 0 for t less than 0. Now when we take the Laplace transform of this one, we will be getting R of S is equal to A. A is constant, and the Laplace transform of t, we know that it is 1 by S square. So you will be getting it as A by S square. Next comes the parabolic signal. So in parabolic signal, it is mathematically represented as R of t is equal to A t square by 2. So that is a general equation for a parabola. So now you have, it will be like this, and this is the time, and here it is, the signal is present only for t greater than or equal to 0. For t less than 0, the signal, this output is 0. Now here, this one you see A t square by 2 for t greater than or equal to 0, and is equal to 0 for t less than 0. Now we take the Laplace transform of this one. We will be getting R of S is equal to A into A, and Laplace transform of t square by 2. That we will be getting as 3 by S cube. So we will be getting it as A t square by 2. You will be getting it as A by S cube. So that is the Laplace transform when you take here. So now we have another signal, that is the impulse signal. So that is generally represented as delta t. So here the impulse signal is like, it is represented like this. Now here this is t is equal to 0. We have t here, and impulse signal means it is present only at t is equal to 0. In arrow, it is a spike present at t is equal to 0. So this is generally, we represented it as delta t. That is the impulse signal. So when you take the Laplace transform, this is basically the Laplace transform, the equation, that is e raised to minus st, integral minus infinity to infinity, e raised to minus st ft dt. That is for finding the Laplace transform. Since it's an impulse function, we know that it is the amplitude, this output is present only at t is equal to 0. And for t greater than 0 and t less than 0, the output is 0. That is what, for delta t is equal to 0 for t not equal to 0. That means that t is equal to 0, we have that delta t. Remaining place, it is 0. So when we take this Laplace transform of this impulse signal, we will be getting it as 1 as the answer. So R of S is equal to, we will be getting it as 1 for impulse signal. So these are the various standard signals which we use for the time response analysis. And the importance of the standard test signals I already mentioned the starting of this lecture. So I hope you understood what are the standards test signals and what is meant by time response of a system. Now we will see the time response of first order system and the time response of second order system in the next video. Hope you understood. Thank you. Thanks for watching.